Kick off. So we've got Ocean 323 and Joel 273373 here. Hi, folks. Ocean 323, you heard from Pete yesterday, and the 373 lot heard from the boat this morning. So I don't need to say very much except hand over to Chris and Christina, who are going to take us on a tour of the ship and what they're up to. How's that sound? You ready to go?
That sounds fantastic. Yeah, so can whoever's manning the camera, can you point me back toward the classroom? Sweet. Hey guys, so can I see a quick show of hands? How many people in the room did not, were not at the 8 a.m. lecture this morning? So how many, only Ocean 323 people do we have? Okay, fair few. So what we're gonna do
like that
this,
next week.
We'll give you a very quick overview of the objectives that have us out here at sea. We've been here on the JOIDES Resolution for about 7 weeks. We've got sort of 10 days of operations left before we sail into Punta Rena. We've got one of the co-chiefs of the expedition here with us now, so we'll introduce you to her. And maybe we'll even let her give you a quick overview of what we're doing out here. When we talked to you at 8 a.m., we just saw the beginning of, so we've come onto a new station right around 8 a.m. We took you guys outside to look at the building up of the part of the drill string that goes right down to the seabed. Right now, the drill bit is hanging about 1,300 meters down in the water, so we're just over 1/3 of the way deploying that string to the seafloor. So we'll go out onto the rig floor. We'll have a look at what the drillers are up to now that they're into those 30-meter stands of drill pipe. And then we'll take you down into the labs. We'll catch up with the bits of sedimentology that we didn't talk about at 8 a.m. We'll run you through some of our physical properties measuring spaces. We'll really give you a flavor for how this drill ship is a massive floating laboratory. We'll talk a little bit about the International Ocean Discovery Program as an entity, sort of a global entity. It's a really cool program that has 24 different countries coming together to cooperate on research that is addressing some of the most important outstanding questions in earth science today. So it's a really fundamental tool for marine geoscience, and sedimentology is a big part of how we unlock those secrets of Earth's past. Then we'll step into the lab I've been working in, that's the biostratigraphy lab, and I'll introduce you to some of my colleagues there. We'll talk about why the microscopic organisms that we recover from the sediment are really important to characterize in real time while we're out here on the ship. We'll hop down to see our geochemistry team for a few minutes, and then we'll come back up here into our planning space, and we'll have a Q&A. So you guys should be thinking about any questions you might have about what we're up to out here. As we go along, jot some little notes down. This is a nice quiet place, so we'll probably wait to take questions until we get back to this quiet area. That'll let us hear you a little bit better. And I think the Wi-Fi connection on the ship is better up here than it is down in the lab spaces. So you can probably hear us better up here than you'll be able to downstairs. Does that sound okay?
All good.
All good. Awesome. So first, for those of you who are enrolled in Ocean 323 but are not taking sedimentology, I'll introduce you quickly to Chris Moy.
Hi, everyone.
This is Chris Moy, or you can introduce yourself.
I'm the course coordinator for 273-373. I'm a geologist in the Geology Department, and my focus is on paleoclimates and sedimentology and stable isotope geochemistry.
Yep, and I'm a paleoceanographer, and I'm split between the geology and the marine science department, and I coordinate Ocean 323, and I really look forward to seeing some of your familiar faces. It's good to see some friends in the audience right now, and to meeting those of you I don't know when we get back to Otago in about 2 weeks. So with that, I'm gonna probably turn over, I can do this. So I'm gonna turn over to Gisela Winkler. This is Gisela over here. Gisela is our co-chief scientist, and it's her vision that has seen the 30 scientists on board the JOIDES Resolution come together for this 9-week expedition.
So, hi, welcome everybody to the JOIDES Resolution. Do you want me to say 2 words?
Yeah, do you want to talk about what we're doing out here?
Sure.
Yeah. All right, so Gisela's going to give you a quick intro to our expedition objectives, and key to this is the part of the world that we're working in right
Yeah, so we started off from Punta Arenas, and we've been on this expedition for almost 8 weeks now. So we left from Punta Arenas, and the overarching theme about this expedition is to study the paleoclimate, and particularly the Antarctic circumpolar current in the South Pacific on up to 8 million year old sediments. And so we picked originally seven different sites that we planned to drill. 3 of them were actually out in the southern central Pacific, out here in the middle of nowhere, pretty much halfway between South America and New Zealand. And we had 3 sites here in the subantarctic, 1 site south of the polar front, and unfortunately, because of weather problems, we couldn't reach. That's the first thing we did in the first month. And then we returned back towards Chile. Now we are really close to the coastline of Chile, about 200 kilometers distance. And we're drilling our 5th site pretty much right here. And what we're trying to do is reconstruct the carbon cycle in the past, variability of carbon cycle, and the strength and changes of the Antarctic circumpolar current and its role in the climate system. Sort of these are the 2 big topics that we are after.
Awesome. Anybody have any questions for Gisela before we take you outside? If there's a handheld mic in the room, Gary, it would be good to circulate it for questions.
I'm holding it. No questions.
No questions?
Okay.
All right.
Sure. So I don't want to take more of your time, but thanks for joining us here, and have fun on the tour.
Yeah, excellent. All right. So, Chris, do you want to?
Sure, I'll lead the way out here.
Lead the way outside.
Let's see here. A hard hat on here.
Yeah. So the next thing we're going to do is take you guys out to take a peek at the rig floor. There are a couple of really handy videos that will explain parts of what happens on the rig floor that we're not able to observe directly out here. And I think we haven't been able to set those up for you to watch in the lecture, but I'll make sure that they get posted to Blackboard for Ocean 323. Chris will do the same for sedimentology, and you guys will have an opportunity to sort of dive in a little bit deeper to how this ship operates from a logistical side or from an operational side once we're done with the tour here. So Chris, do you want to take us outside?
All right. Here we go. It's going to be loud out there, but I'll do my best to kind of speak into the microphone on the side of the tablet there. Here we go.
Okay, guys, so for those of you who've gone through Otago's geology program or who took EOS 111, you might remember that we did a lab using marine sediments.
Hey, Christina, do you want to get closer to the mic?
What's that?
Get a bit closer to the microphone.
Right, so we did a lab in EOS 111 where you looked at a bunch of pictures of drill cores and you used a data table to determine what kinds of sediments accumulate on different parts of the seafloor. And so together we made a global map of seafloor sediments, and all of those data and all of those cores were collected by the drill rig you're looking at right now. Right, so what you can see looking up into the dark is the derrick pulling this 30-meter stand of drill pipe into position. We've got some really excellent rig hands on the JOIDES Resolution. Some of these guys, one of our tool pushers in the white shed back there, has been working in scientific ocean drilling since the 1980s, right? So probably before even some of your parents were born. These guys were out here collecting sediment cores to use to reconstruct Earth's history. So what you're looking at right now, I don't know if you can see, this is the iron roughneck, big red piece of equipment. It spins. We have pre-assembled these 30-meter lengths of pipe have a diameter of somewhere on the neighborhood of maybe 15 centimeters, and they're being lowered into the seafloor 30 meters at a time. Our seafloor depth here is about 3,300 meters, so we need 100 of these 30-meter stands to get down to bottom, and these guys work at about a rate of 400 meters per hour. You can see they're a well-oiled machine, like a ballet down there. So they're so the top drive is going to drop this next stand of pipe into place.
So it is transferred from the top drive to the rig floor here. So each of these stands of pipe weighs close to a ton. And so we're probably about maybe 40 stands of pipe down right now. And so you can see how quickly these guys can do it. It's pretty remarkable. Okay, and so when we're coring, we're setting a almost 10-meter long steel barrel with a plastic core liner inside down through that drill pipe all the way to the seafloor. And then we're essentially filling that drill pipe full of seawater and allowing the pressure to build up to the point where we actually shoot the bottom of the core into the soft sediment below. And so this is going on kind of at 10-meter increments. The core is brought back up through the drill pipe and essentially disassembled on the rig floor right in front of you. All right, we're going to go downstairs and take a look at the rig floor. Okay, so you can see the iron replic again attaching stands of pipe with one another. And essentially, once we've collected a core, these guys will open the pipe up, take the core barrel out, and lie it along the floor here off this stand, and pull out the core liner. Our piston cores that we use to collect the sediment are assembled over here, so they're lined up, ready to go. So once we hit the seafloor here, we'll put plastic liners in the core, and those will be lowered through the drill pipe down to the seafloor.
All right, so inside each of those metal liners, when we start to pour, they're loaded with these 10-meter lengths of plastic tubing. You can see these are on much smaller diameters still than the metal pins over there. And so when each core is pulled up from the seafloor, it sort of comes up on the line, and the drillers pop it out and deliver it down onto the catwalk. This stand of core is carried by our technicians. We have some really excellent geoscience technicians down on the ship. They'll carry this long piece of core all the way to the end of the catwalk. You can get a feel just looking down here how long 10 meters is, right? So there's Chris at one end of the core. Here you are at the other end of the core. These pieces of core liner full of sediment get laid out all along this table. The technicians use these tools to section them into 1.5 meter long pieces, and then they get a cap stuck on each end, blue for the sky, clear for the bottom, caps on each end. They're sealed shut in a permanent way. And then once the entire queue, so all the sections get measured off by rulers. And then once they've been cut into these 1.5 meter long sections, they're carried inside where they start their journey through all of the instrumentation and the core description team, the biostratigraphy team, all of those things. So this will take you inside. Oh, actually, before we head inside, we'll have a quick look. So these are some of the drill bits that are used in the sediment. Chris described to you how that core barrel is pumped full of seawater. That seawater generates enough pressure that pins are sheared, and the core barrel is shot through into the sediment. So that metal piece is shot out from inside some rotating barrels like this. It comes shooting up into the sediment, and then once it's lodged as far as it can go, this drill bit drills down around it so that it will come up to the end of where that core is, and then only once we've drilled around the outside of the core barrel is it pulled back up to the surface. So we're not actually rotating as we drill, we're using that force of the piston to drive this essentially like a knife into the sediment. But if we were out here trying to drill sort of the oceanic crust or trying to drill harder rock, we would be using spinning bits like this. So there are a lot of different kinds of drilling that we could do with the JOIDES Resolution. We're out here drilling for sediments, trying to find paleoceanographic records or records of oceans or of Earth's past climate. But this ship does all kinds of research. And in Ocean 323, we'll talk about a variety of the different major discoveries about the way the planet operates that have been made in this very ship. So Chris is going to take us inside. We'll continue our tour.
All right. So once these cores are collected, this is where our core flow begins. One of the things that happens here is that our it's not gonna open. It's locked into position. But one of the first things that happens here is that our individual core sections goes into this laser engraver here, and so a key essential part of the core flow begins with making sure that each of these sections are labeled appropriately. And so we have an onboard database that keeps track of all the core sections that are collected. But importantly, we also make sure that each of the core liners are engraved with a specific ID number, as well as an overall label to tell, which essentially section is which. And so that's done within this instrument here. After that, we have a number of track systems on board here that we essentially take our whole cores and place them through. And we get oriented here and see if I can find one that works well. Just 1 second. Gotcha, Jim. Thank you. So this is an example of our 150 centimeter section, and one of the first kind of routes it takes through here is through a series of sensors here that records the physical properties of the whole sediment. And this is really valuable because we get some most instant information on kind of major changes in lithology from the whole round sediment core. And so we have an instrument and a sensor here to measure the gamma ray density, or the density of the wet sediment inside the core liner. We have an instrument here that can measure the magnetic susceptibility of the sediment. And then we have a sensor here that can measure essentially the velocity of sound through the sediment. And these are kind of initial measurements that will get, for one 10-meter core section, even at a very coarse resolution, we'll get within 30 or 40 minutes. And this is really valuable because on this cruise, this is really a paleoceanographic focused cruise. And so what's really required is that we have a full continuous record without any core gaps. And so even when we're drilling in calm seas, those breaks between the 10-meter long sections, they'll have a little bit of a gap and they'll have some drilling disturbance, even minor drilling disturbance at the top of those cores. And so we have somebody on board that's sailing as a stratigraphic correlator that's making sure that essentially we have a full and continuous record. So we'll drill down to one depth in one hole, we'll call that hole A, and then we'll move over maybe about 50 meters or so, offset the cores a little bit. And this instrument here will tell us essentially if we're getting all of that complete recovery. And we can see that in the variations in density and magnetic susceptibility. So we're going to introduce Shinya now. Okay, Shinya, come on over. So Shinya, you met earlier today. He's a sedimentologist on our team.
Hi.
He's from Japan, from JAMSTEC. And one of the instruments that he's been running within Team Sedimentology is this relatively new instrument here. It's another track system that can help us look at density changes within a core. So let's see. So you want to take us through some of the things that you've been doing? Okay. So one of the things we have here is essentially it's an X-ray machine, and what we can do is place either the half round or the whole round into the instrument here. Throw that one on. Okay. Sorry, dummy one. get out of the way here.
Yeah. Hi. Here is I'd like to show the X-ray core scanner of JOIDES Resolution. Here is the entrance of core, and core is moved to this way. And here is the exit of core. So core moved from here to there, and at here X-ray images are taken here, and every 12 centimeter we take X-ray images, and when we take images, these pictures are saved in this computer and automatically updated to the system, and we can see the X-ray images in every computer of this ship. It's a very convenient system. And so when we describe the cores, we cannot see the inside. So okay. Here is an example of X-ray images. From X-ray images, we check the 2 points. One is the IR, ice active debris, the black point. It is this zone is carried by sea ice or glaciers. This is a very important proof of existence of sea ice or glaciers. And the other point is bioturbation of sediment. And this is a mixing of sediment by the benthic organisms. And by the X-ray images, we can see the funnel of benthic organism or trace of their organism. This is very helpful and for describe the core precisely. Yeah.
Excellent. Thanks.
Yeah, thank you.
Fantastic. All right. So I'm gonna wrap up here and just leave you with this. You know, these sensors are really helpful. They're really valuable, and you might have heard at Otago we've developed and we're building this core facility, and many of the analytical tools that we have here on board on the JOIDES Resolution are tools that we also have at Otago. And so again, we have a big kind of research focus that's based on using sediment cores to look at past environmental, climate, and tectonic change. And these instruments are really valuable, and we have the capability at Otago to also do some of these measurements. I'm going to take you and pass you over to Christina, and she's going to introduce you to another Christina.
Yeah. So as Chris just mentioned, we have a lot of these same tools at the University of Otago. And for those of you in Ocean 323, when we go on our field trip to Stewart Island, we'll actually do some sediment coring, and then we'll take those cores back to the University of Otago. And we'll use some of these very same systems to characterize the cores that we collect in the field. And you'll have an opportunity to do a project, a little research project, in the second half of the semester using these same sorts of systems. Now, you met Shinya. He's at Jamstech in Japan. Chris and I are at Otago with you guys. This is a really international ship, right? So I'm going to take you now to introduce you to another Christina. She is the primary user of these physical properties data that are collected in that lab over there. And she's going to tell you a little bit about the importance and how we ensure we have this complete record of Earth history or ocean history by drilling multiple holes. So, Diane, take it away.
Okay. Is there any way you can see the screen or not? Is it too hard to see it? No, you can sort of see it. Okay. So I think Chris mentioned that you drill multiple holes. And when you scan, and it's for each hole, you gather cores that are about 9.5 meters long, and then you go down and you get another core and then another core. But there's gaps between those cores. And when you scan the cores and you look at the data, you see that right there represents one core of data. This is magnetic susceptibility data. And then the core next to it, let's see, there's cores next to it, all the way going up. These are basically 3 holes. And I have to correlate across the holes those signals and piece together a continuous record from the top to the bottom using this computer program essentially that allows me to visually connect features from one curve to another. And that's the way we build a continuous splice, it's called a splice record down core, and it also guides us after the, which is the most important thing really, it guides us after the cruise to be able to sample the cores in such a way that we have no gaps. So we sort of jump from one hole to the other, and that way we get a continuous record of sort of sedimentary sequence from the top to the bottom of the site. So believe it or not, that's what I do 12 hours a day is to correlate these records because it's a huge amount of data. And it's pretty complicated, especially in some sites, and so I have to use multiple types of data. The susceptibility, the density, color reflectance, the kinds of things that you're seeing being measured in this lab, I use kind of all of them together to build this splice. Yeah.
Awesome. All right, so once all this physical properties data are collected, the next thing that happens to this whole round core is that it gets carried into the splitting room. And in the splitting room, it gets split into 2 even sections. And those are the sections that you would have seen in the core photos that we used for that EOS 111 lab. So this travels into the splitting room. It's loaded onto the track. Many of our cores are collected in a way that's oriented, so we know how they sit relative to Earth's geomagnetic field. And then you'll see that there are 2 lines on the top, 1 line on the bottom, and they're split longitudinally, right? So they sit down against the splitter is closed, and then we have 2 blades and a little cheese wire that cuts through and runs smoothly along the length of the core. As soon as they're split, so this is something that our technical crew do. As soon as they've split and tidied up the cores, they get carried right through there into the sedimentology area, where Chris will show you that same.
All right. Fantastic. So here we are back at the. Well, this is the main hub of the core lab here. This is the sedimentology description table. And so we showed this a little bit this morning, but for the Ocean 323 people that are joining us now at noon, this again is really the center of activity, especially when a new core at a new site comes on deck. Typically you'll see a big part of the team surrounding these things, where the archive half, essentially the half of the core that doesn't get sampled on board is essentially presented. And it's at this table that the sedimentologists, the sedimentology team, myself and Lee and Shinya and Julia, who you met earlier, it's our job again to describe the sediment that comes on board. And we're interested in lithologic changes, and we're interested in all types of variations that we see in the stratigraphic record. Again, we're correlating here between other holes, and so we're building up this composite stratigraphy. So it's critical that we can go through and evaluate the sediments at a centimeter scale. This again is a core that we were looking at this morning. It represents a snapshot through an interval of time in the Pleistocene where we're seeing these really high amplitude glacial, interglacial cycles. And so you can see some of these variations. They're quite clear even in the color of the sediment. We're down here at what's at the base of one of these 9.5 meter long cores. Here it's subdivided into 7 sections, right? And so over at the top left-hand side over here is the top of the record. And so the youngest part of the core here. And so we're going up through here, and one of the first things you see is a pretty large dropstone, limestone that was deposited either by sea ice or by a floating iceberg. In this setting, close to the Chilean margin, it's probably an iceberg that had some debris stuck to the bottom of it, and it passed over our coring site. As we go up towards the middle of the core, you can see this very, very light colored interval. And this is a section that's dominated by one of the marine isotope stages that Julia talked about this morning, marine isotope stage 11. It's one of these really warm interglacials that captures the Pleistocene, right? So the last million years of Earth history is really characterized by these high amplitude changes in glacial ice extent, as well as sea level rise. And we talk about that a lot at Otago in a lot of different geology inter science classes. And this white-colored material is essentially made up of nanofossil remains, essentially coccolithophores that were really prevalent at the time over the drill site. And then we come out of the interglacial interval, and we go back into another glacial interval. And you can see right off the bat, pretty soon after, we get another drop zone appear. So ice is expanding out of the Andes. And so one of the ways that we certainly describe that, we use many of the tools that we showed you this morning, and that many of these tools that you should be familiar with first-year geology classes. But then we have other ways to talk about or to look at how these sedimentary lithologies are distributed throughout the sequence, and that's some of the things that we're doing here in the sedimentology group. And one of them is this instrument over here, and Lee has been running this instrument today, and he can give you a little description of what this thing does and how it's valuable to us.
Everyone, nice to meet you here. As you can see, we're still busy deal with the course because we still have lots of section need to be done. And as you see, already saw the sediment. According to our naked eye, it's totally like gray, darkish gray, like very gray stuff. But still, if we use other instruments, then we can see the details of the change of that. So that's why we have a section half multi-sensor log here. So in these two detectors here, we put a section over here and put a thin film on top of it to prevent the detector to touch the sediment directly and the contamination between the samples. And two detectors here. One is for the color reflectance, like a total reflectance of light and different, or the reflectance of different wavelengths and different spectrum of light. And the other one is the magnetic susceptibility point sensor. So these instruments can help us to have a higher resolution, non-destructive measurement through the section, like every 2 centimeters or per centimeter. So the data we generate here, we can see from the monitor over here. I already put up here. So that's the pictures that we took from this section, just the sediment section you have saw, from section 7 to section 2 here. And we have the description about the lithology change. Then we have the result from the color reflectance, like a B star here. The B star in the purple line. The B star is a ratio between yellow and blue light. So you can see the ratio of B capture these change very clearly here, like a positive excursion around here. And also in the same time, the magnetic susceptibility point, from here you can see the very low magnetic susceptibility over here in the interglacial time. Possible reason is that the lower terrestrial sediment input and higher biogenic roots. So according to these data, we can not only through our naked eye and all the basic instruments, but we can also have these high resolution and non-destructive correlation data for the stratigraphic correlations. Yeah. So that's it.
That's fantastic. Thank you. That's really
So,
nice.
I'm
going
going
to
to
pass it over to Christina here.
So I'm going to pick up on this idea that we have biogenic material in the sediment, right? So Chris has showed you how the stratigraphy goes from something that's dominated by particles, by triginous particles, into a lithology that's dominated by biological particles. So in this core, our biological constituent is primarily calcareous nanofossils, right? So tiny little coccolithophores. And now I'm going to pick up on that, and I'll take you into the biostratigraphy lab where we use the species composition of those biogenic sediments to learn something about the environment that the sediment was deposited in, and then also about the age of the material. So if you come with me, I'll come in. We have paleomagnetism. So you're all familiar with paleomagnetism. We're having those measurements made directly here on the ship. So that's one of the tools we use to tell time out here. And then the other tool we use for telling time is the fossil composition. Sam, we've got a step. The fossil composition of the biogenic part of the sediment. So this is the area that I work in, and you can see I've got some colleagues who work with different fossil groups. I'll show you the work that I'm doing first. So we spend an enormous amount of time on microscopes in here. and mostly looking at slides as the sea state rises and falls. So every single new core that arrives on deck, the very first thing that happens is the biostratigraphers grab a tiny little piece of that, and we make, for the diatoms, the group I work with, and the calcareous nanofossils, the group that made the sediment white out there, we make little smear slides. So at this point in the cruise, I have about 250, 300 smear slides that I'm going to be taking back to Otago with me. And then we also have people who are looking at the foraminifera, or forams, and those folks are taking a big piece of sediment and washing it through a sieve. Now, what I see when I look down this microscope, we can get a new image here. So I get a first glance, almost instantly, when the core comes on board, before it's even been run through any of those whole round loggers, I get a peek at what the sediment is made of. So this is a sample that came from one of our Central South Pacific sites, and just looking at what's under the microscope here, I can instantly tell you how old the sediment is, right? So I see this species here, and I know that this was alive between about 2 million and 3.8 million years ago. And then I can look a little bit further, and I see a species here, and this was alive between 1.2 and 4.2. So that gives me a narrower window. And I have another thing over here. This one has a last appearance of 2.4. So just by looking at this single image, you know, it's maybe the first field of view that I see under my microscope, I can immediately tell you that the sediment in this core picture, this was from core 15 at one of our sites. So, you know, maybe 140 meters down below the seafloor. Just the single field of view tells me immediately that the sediment is somewhere between 2.4 and 3.8 million years old. The other thing it tells me, if you look here, I have a lot of this tiny little circular thing here, right? So this is pretty abundant. And this is a species. Here's another one up here, a couple more over there. This is a species that really likes warm water, right? So this grows the most abundantly when the sea surface temperature is between sort of 9 and 13 degrees. And so when I look at this sample, not only do I know exactly how old the sediment is, I also have an instantaneous impression of what the climate was like when these diatoms were settling to the sea. So we have, as I said, we have lots of people on this team. Over here we've got Mariam. She's originally from Spain, has been living in Germany, and is now moving to the UK. Over there we've got Raj from India, who works with benthic forams, and we have Igor from Brazil, who works with planktonic forams. We also have somebody who works with radiolarians from Brazil. He's on the opposite shift, so we're in here for 12 hours a day from noon to midnight. This team of 4 people is putting all of our information together into a picture of the age of the sediment. We're generating these data, right? So we know the depth in the section. Each of these points is an age of a different, either microfossil or a paleomagnetic reversal, or a place where we can correlate to one of the global isotope reference curves. And all of that information comes together to give you a picture of the age versus depth and sedimentation rate of this location. So you can see on this board up here that our last site, we didn't have a ton of biological material. That's because it was pretty overwhelmed with all of that sediment being sloughed off the Andes in Chile. I think, Mariam, do you want to give us a quick look at what you're doing in the water column? So we've also got, in order to make our best interpretations of what's happening in the sediment, we have to have a really good understanding of what goes on in the modern system. So Mariam and her co-nanofossilista, so I said that we work from noon to midnight, and then there's another team of 4 biostratigraphers who come in, we high five every day at noon, we high five every day at midnight, and we swap teams, and the work just goes on and on and on. So Mariam and her counterpart on the midnight to noon shift have been taking samples of the surface ocean, of water. They just toss a bucket over the side and haul it up. And by doing that, they've developed a really good picture of what's going on in the surface ocean at the places we're coring.
So here we can see some of the nanofossils. So we took the bucket, we filter 2 liters through a cellulose and 2 liters through polycarbonate membranes with a vacuum pump, and then we retain the algae, some diatoms, and copelissophores. These are algae that create small carbonate platelets. Here we can see Emiliania huxleyi, the very well-known and cosmopolitan species that is across the whole, all the oceans, even in polar waters. But here we can see also like the amazing diversity that we can observe in polar waters. So these are some of the specimens, and I want to show you. So here we can see our track. We started here in Punta Arenas and made a triangular shape. So we have a really nice transect that covers different environments and with different temperatures and different chemical parameters that we have been monitoring. So we can really link and see where species lives in which habitat and reconstruct the modern day conditions.
Mariam, I have a question for you. So they just looked at the stage 11 core from our last site on the table. Are any of these species found in stage 11?
No, they are extinct, but if you give me a second, I can really show you stage 11 here. So this is a bit improvised. So here I'm using a polarized microscope at 1000 magnification, and we put a bit of oil to see the image better. And what we see nothing so far. Oh no, this is not very good. Mix 11. Okay. Okay, we see this species during Miss 11, the carbonate white chalk layer you saw before is made out completely of this small Differocapsa called Caribbeanica, and normally it's really, really rich. But in this case, we are in the transition, so we are not purely in the chalk. I was like not ready for Miss 11, but but it's a similar species to Emiliania. It's like the great grandparents from Emiliania.
Awesome. Thank you, Mariam.
No worries.
All right, so what we're going to do now is take you guys down into the geochemistry lab. We'll say hi to the geochemists for a couple of minutes, and then we'll just pop into the conference room for maybe 3 minutes at the very end. Does that sound good to everyone? All right, so here we go. You can see Raj here as we walk past. So we've got an SEM on the ship, and he's making images of the benthic forames. Raj is one of the happiest people on the boat in this expedition. He's found 3 or 4 new genera of forams just in the last few weeks. And so he has a lot of new species to name when we get back to our home institutions. Yeah, so we might lose the connection in the stairwell, but we'll pop right back in. Keep going, Chris.
We've caught the chemists in action here. This is Lisa. Lisa's a graduate student at Stony Brook University in New York, and she's one of our chemists on the team here, and she's going to explain some of the things.
So Lisa, we only have a few minutes left.
Okay. So I'll just go through what I'm doing now. Very exciting. I'm taking these glass tubes that have water, and I'm flame sealing them. Some of them don't look very good, but basically you just melt the top. But we're sealing it so that they don't evaporate while they're sort of in transit to the lab that they're going to be.
Where the water came from?
Yeah, so this is pore water from the sediments. So can't see it very well, but yeah, we squeeze the sediment cores with these things. These are our squeezers and we load a piece of sediment, in one of these in there, and then we put this, it's all titanium, in there. And then
which pressure do you use to?
So it depends. With a really like fluffy sort of diatom rich stuff, we use 3,000 PSI, I guess, pounds per square inch. But with the clay that we were just analyzing, there was so little pore water, we got up to 25,000 PSI.
Wow.
We barely got any pore water. So yeah.
And so you guys are making a number of measurements, and you'll make other measurements on the water afterwards. What are some of the things you're trying to find out with the pore waters?
Yeah, well, I mean, for example, some of the things that we do in this lab are pH and alkalinity, and then we analyze other elements like iron and manganese, sulfate, phosphate. And then looking at all of those together, you can kind of determine some of the different chemical reactions that might be happening in the sediment. So like if there's iron or manganese reduction, that's an anoxic remineralization process, and that has an effect on the alkalinity. So, you know, if you see iron increase in the pore water and you also see a change in the alkalinity, you can kind of piece that together to try and understand what's happening.
Fantastic. Awesome.
Thanks a lot, Lisa. Yeah.
Awesome. All right, we'll take you back.
All right, so we're going to pop into the conference room. We know that time is getting tight, but we want to make sure that you guys have a few minutes to ask us any questions you have. Also, we caught us in the middle of a ping pong tournament and a cruise logo T-shirt pressing party. So let's probably just collect ourselves.
This is our cruise logo. It sums it up. You know, being out here in the high southern latitudes for the winter solstice, very far away from land. We've had a lot of musicians on the boat, including a talent show. All of our friends, Eden the albatross, are flying around, so you can kind of see, you know, where we've been or what we've been up to for the exactly.
So Chris and I are going to pull up a couple of chairs here.
There we go.
And we hope you guys have some questions about what we're up to. We know that was a pretty whirlwind tour, but now we can see you, and we would love to tell you the things you're actually dying to know. So Gary's got a handheld microphone. Please don't be bashful.
We only have 3 minutes.
I see a hand. Let's do it. Let's do this thing. Make Gary run.
Okay. I was wondering, like, how y'all stay in communication with the crew of the ship, and like how y'all work with the crew to plan like your cruise track and like sampling plan and everything.
Right. So one of the things about an International Ocean Discovery Program cruise is that it's the culmination of usually about a decade of preliminary research. So before we come out to sea, there have been lots of geophysical surveys performed. Usually there have been some pilot cores collected that are pretty shallow, but they give us a sense of what we might expect to see in the sediment record. And so we know exactly where the ship is going to go before we get to sea. We know exactly because we're in the 51st year of scientific ocean drilling right now. We know exactly how long it takes to trip the pipe down to any seafloor depth. We know about how long it takes to drill to any depth. So before we even get on the ship, we have a really detailed time plan about how many sites we can drill, how many holes we can drill at each site. The only time that gets disrupted is when the weather is uncooperative, and we've had some uncooperative weather out here. So when that happens, the co-chiefs talk really closely with the captain of the ship. The whole ship is outfitted with telephones, so we can call the rig floor at any time. There are PA systems, so every time a new core arrives to the surface of the ship, there's an announcement around the entire vessel that there's a core on deck, and that brings all the scientists running out to the catwalk to collect their samples and take measurements. So we're constantly monitoring for hydrocarbons. We don't want to drill in a hydrocarbon environment out here because it's environmentally dangerous and it's operationally dangerous. So every single core that comes up, we measure it to make sure there's no hydrocarbon present before we continue to drill the next.
Yeah, so we have a lot of restrictions. We can't, like, even when the weather was poor, we couldn't like just go off and drill anywhere we wanted. You know, we had to actually drill in a very prescribed way to a certain depth. And Andrew, who's sitting there on the front row, he sits on the committee that helps make these decisions by looking at seismic data and evaluating essentially how deep can drilling be done and if there are any potential dangers in doing so.
Yep. So every site has been vetted by a bunch of experts before we even get on the boat.
Yeah.
Any other questions?
We got time for one last burning question.
And if anybody wants to stay a little bit late, we'll hang out.
We probably
Surely
have
someone's
to
got a question.
room. Nothing more? So one last question from me then. When you abandoned that site south of the polar front, did you manage to get any other sites that would give you that information, or are we going to have to mount a whole new drilling leg to solve that problem?
We will have to mount a whole new drilling leg to solve that problem. Yep, so we're already, when we had to abandon that site south of the polar front, we already have people on the ship. There were a series of alternate sites also in that region, so we've got a plan being hatched right now to put a new proposal in that will return to work in that part of the Southern Ocean. Those of you who were in the 8 a.m. lecture, when Chris showed you our sort of where our sites sit relative to the frontal circulation around the Southern Ocean, will know that this is a really challenging place with respect to climate. So the biggest waves that passed that site that we had to abandon while we've been at sea were 14 meters, according to the wave model. And that means that you need some time to be able to adapt to those conditions. On this expedition, we didn't really have that cushion built in. So we know the next time we come back that we need to make a plan that's sensitive to weather.
Okay, cool. Thanks, guys. We'll disconnect now,
Gary,
and
hold
talk
on, Gary.
to land.
So the last thing I want to say before we take off is to put in, just put a bug in all of your ears and all of your brains. New Zealand we've been a member of IODP since 2008, which means we're members in a consortium with Australia. And that means that everybody in New Zealand has access, they have opportunities to apply to sail on the JOIDES Resolution. You can do projects based on samples collected by the ship, and you can be involved in workshops and projects and sort of training opportunities that are hosted by the International Ocean Discovery Program. And although this expedition, as Chris said, at 8, is the last one in a series of expeditions in the South Pacific. And they've studied a lot of different things. You know, some of them have been examining how plate tectonics operate off the North Island. So looking in at the Hikurangi margin, there are proposals in the works right now to drill down south at the southern end of Fjordland to look at the subduction zone down there. And there are always opportunities for students to get involved in scientific ocean drilling, right? So we have a lot of PhD students on the ship with us. It's due back in the New Zealand region, hopefully in 2023. Hopefully that'll be a time that we're back in this part of the world, collecting the cores we weren't able to get on our current expedition. And for some of you, that'll be really prime time to be moving into postgrad. Anybody who thinks they might be interested in postgrad in this kind of work, there are likely to be opportunities to get students on the boat. So if you like this kind of stuff, when Chris and I are back at Otago, come in and have a chat with us about how to best track yourselves to get involved in research like this. There are so many things to discover, and you guys are going to be the ones who lead the next wave. So,
okay, we'll see you in a few weeks, guys.
Yeah, so we'll be back in 2 weeks. We'll
You're in
see
good
you
hands
then.
there. We'll see you then.
Yeah, and thanks, Gary, for introducing us.
Yeah.
Okay, see you guys.
See ya.
Bye-bye.
Bye, Sarah.
Bye, guys.
Bye, Michael.
Bye, Andrew.
Bye, Andrew.